A 9.6 billion-year-old object just tore through our solar system at 130,000 miles per hour. It's spitting out pure nickel with no iron. It has a jet pointing directly at the sun when it should be pointing away. And the odds of its trajectory lining up with our planet's? 1 in 20,000. Scientists are calling it impossible, and it gets weirder. Back in 2017, we spotted our first interstellar visitor. Oumuamua. It was strange, sure. No tail, weird shape, moved in ways we couldn't explain. We thought maybe that was just what interstellar objects looked like. We built our entire understanding of alien visitors around that one data point. Then 3I divided by Atlas showed up, and it broke every single rule. This thing is faster than anything we've ever recorded in our solar system. It's older than almost everything we've ever studied. It's doing things with chemistry that we thought only happened in factories on Earth. And by the time you finish watching this, you're going to see why some scientists are having very uncomfortable conversations about what this object actually is. We're going to walk through every bizarre detail. The industrial metal emissions, the backwards jet, the impossible age, the trajectory that shouldn't exist. And by the end, you'll understand why this comet is forcing us to completely rewrite our understanding of what's out there in the galaxy. Because when the universe sends us something this strange, either our physics is wrong or we're looking at something we've never seen before. Let's start from the beginning. On July 1st, 2025, astronomers in Chile were doing routine sky surveys. Just another night of watching the cosmos. Then, something appeared in their telescope feeds that made them do a double take. A bright object, moving fast, really fast. They ran the numbers on its trajectory and realized immediately that this wasn't from around here. The object was designated 3I divided by Atlas. That I stands for interstellar. This was only the third confirmed visitor from beyond our solar system. The first was Oumuamua in 2017. The second was 2I divided by Borisov in 2019. Both of those were strange in their own ways. But 3I divided by Atlas, it was about to make them look normal. The first thing they noticed was the speed. This thing was booking it. When they calculated the velocity, they got a number that seemed wrong. 130,000 miles per hour. That's 58 kilometers per second of hyperbolic excess velocity. For context, Oumuamua came in at 26 kilometers per second. This new visitor was moving more than twice as fast. But it wasn't just fast. It was following a trajectory that defied probability. See, when objects move through space, they follow what's called an orbit. Even when something is just passing through our solar system, it still follows a curved path around the sun because of gravity. We measure how curved or straight that path is with something called orbital eccentricity. A circle has an eccentricity of 0. An ellipse is between 0 and 1. Anything above 1 means the object is moving so fast it's going to escape forever. It's called a hyperbolic orbit. Oumuamua had an eccentricity of 1.2. That was considered extreme at the time. It raised eyebrows. 3I divided by Atlas has an eccentricity of 6.137. Think about that for a second. That's more than 5 times higher than Oumuamua. This object's path is so straight that if you drew it on paper, you'd struggle to see any curve at all. It's like the comet looked at our sun and said, "I'm not here to visit, I'm just passing through." But here's where it gets really weird. Despite following this nearly straight line trajectory, the object is positioned almost perfectly within the plane of our solar system. That plane is called the ecliptic. It's where Earth and most of the other planets orbit. The ecliptic is basically a flat disk, and most of the action in our solar system happens within a few degrees of it. 3i divided by Atlas is inclined at 175.114 degrees. That means it's moving retrograde, backwards compared to the planets. But here's the kicker. It's only 4.886 degrees off from the ecliptic plane itself. The statistical probability of an interstellar object randomly arriving with that kind of alignment? About 0.005%, 1 in 20,000. What that means in practical terms is this. 3i divided by Atlas has perfect access to the inner planets. It can make close approaches with minimal energy. And it did exactly that. In October 2025, it passed within 0.19 AU of Mars. That's closer than many spacecraft missions. It also got within 0.36 AU of Jupiter and 0.65 AU of Venus. When astronomers calculated the odds of all of these geometric coincidences happening together, the speed, the alignment, the planetary encounters, the numbers became vanishingly small. Some researchers started noting, half joking but not really, that this would be an optimal configuration for a hypothetical probe studying the inner solar system while trying to stay hidden from Earth. Because there's another detail. When 3i divided by Atlas reached Perihelion, its closest approach to the Sun on October 29th, 2025, it was positioned at a solar elongation of only 12.8 degrees. That means it was directly behind the Sun from Earth's perspective. Ground-based observation was nearly impossible. The thing, deliberately or not, timed its closest approach to hide behind the sun day. The probability of that specific alignment? About 7%. Not terrible on its own. But when you combine it with everything else, the cumulative odds become astronomical. So right out of the gate, before we even start talking about what this thing is made of or how it behaves, we're dealing with a trajectory that seems mathematically designed to do something very specific. Either we're looking at the luckiest random chance in cosmic history, or something else is going on. And that's just the beginning. Let's talk about age. When we spotted Oumuamua, scientists estimated it was probably around 1 billion years old. That's ancient by Earth standards, but relatively young in cosmic terms. Our Sun is 4.6 billion years old. The universe itself is 13.8 billion years old. So Oumuamua was a relatively recent ejection from some stellar system, probably formed in an environment not too different from our own. 3i divided by Atlas is in a completely different league. Researchers traced its trajectory backward through the Milky Way. They integrated its orbit through the galaxy's gravitational field, running the simulation for 10 million years, comparing its path with 230,000 local stars from the Gaia satellite catalog. They were looking for a home system, some star it might have originated from. They found nothing conclusive. But what they did find was something far more interesting. Based on the object's motion, particularly its vertical excursions from the galactic plane, they could estimate its age using Bayesian statistical methods. The median age they calculated was 9.6 billion years. The 68% confidence interval puts it between 7.8 and 10.3 billion years. Let me put that in perspective. 3i divided by Atlas formed approximately 9.6 billion years ago. The Milky Way galaxy is about 13.6 billion years old. That means this object formed when our galaxy was barely a third of its current age. Our sun didn't even exist yet. Earth was still 5 billion years in the future. This thing has been wandering through interstellar space since before our entire solar system formed. The era when 3i divided by Atlas was born is called cosmic noon. It was a period of intense star formation when the galaxy was young and turbulent. The Milky Way's thick disk, an older population of stars that orbit above and below the main galactic plane, was actively assembling through violent gas-rich mergers. Stars were forming at a breakneck pace. It was a completely different galactic environment than the relatively calm, thin disk that would later give birth to our Sunday. This object is 3 times older than 2i divided by Borisov. It's potentially 30 times older than Oumuamua. And that raises some profound questions. How does something this old survive? Think about what this comet has been through. 9.5 billion years of wandering through interstellar space, cosmic rays bombarding its surface, micrometeoroids colliding with it, thermal cycling between the freezing cold of deep space and the occasional warmth of passing near stars. Most objects would be pulverized, eroded, or completely depleted of volatiles over those timescales. Yet, here's 3i divided by Atlas. Still intact, still active, still outgassing material like it formed yesterday. The survival of this object across such vast timescales makes it an irreplaceable time capsule. It carries material from the galaxy's formative epoch. The chemistry locked inside this comet is from an era we can barely study any other way. We can look at distant galaxies through telescopes and see what cosmic noon looked like from the outside. But 3i divided by Atlas is a physical sample from that time. It's like holding a piece of the young Milky Way in your hand. The kinematic analysis also revealed that 3i divided by Atlas originated from the thick disk population. These are ancient stars with different compositions than younger stars like our Sunday. They're metal poor, meaning they have fewer heavy elements because they formed before multiple generations of supernovae had enriched the galaxy with metals. If 3i divided by Atlas formed in that environment, its chemistry should reflect those primordial conditions. And as we're about to see, its chemistry is problematic. So we've got an object that's impossibly old, impossibly fast, and following an impossibly precise trajectory. Already, that's enough to make scientists nervous. But then they started looking at what this thing is actually made of. And that's when the real problem started. Let's talk about comets for a second. We know what comets are supposed to look like. They're dirty snowballs, basically. Ice mixed with dust and rock. When they get close to the sun, the ice heats up and sublimates, turning directly from solid to gas. That gas carries dust particles with it, forming a cloud around the nucleus called a coma. Solar radiation and the solar wind push this material away from the sun, creating a tail that always points away from the solar direction. That's comet physics 101. We've observed thousands of comets. We understand the basic rules. Ice heats up, gas flows out, tail points away from the Sunday simple. 3i divided by Atlas decided those rules were optional. In July 2025, the Hubble Space Telescope turned its cameras toward the comet. The images they captured showed something unprecedented. There was definitely a coma. There was material streaming off the nucleus. But there was also something else. A jet of material extending from the object's leading edge. Pointing toward the Sunday, an anti-tail. Harvard astrophysicist Avi Loeb described it like this. Witnessing this phenomenon was as shocking as photographing an animal your family thinks is a street cat, only to see a tail coming out of its forehead. Think about what that means. Comets don't do this. The physics doesn't allow it. Solar radiation pressure pushes material away from the Sunday. The solar wind blows outward. Everything should be streaming in the anti-solar direction. Yet here's 3i divided by Atlas with a forward-pointing jet, actively emitting material toward the Sunday. The jet stretches approximately 10 times longer than it is wide. It's not a diffuse cloud, it's a directed emission structure. Something is causing material to flow preferentially in one specific direction, and that direction happens to be sunward. Standard cometary outgassing models can't explain this. Some researchers speculated it might be due to unusual rotation patterns on the surface. Maybe the nucleus is spinning in a specific way that channels emissions forward. Others suggested there might be subsurface volatile reservoirs with asymmetric release mechanisms. Maybe pockets of trapped gas are venting through specific cracks or vents on the leading edge. But here's the thing. Those explanations require very specific, very unlikely configurations. The rotation would have to be just right. The surface structure would have to be precisely arranged. And even then, fighting against solar radiation pressure to create a sustained jet pointing directly at the sun, that takes energy. A lot of energy. Where's that energy coming from? Nobody has a good answer. And when you combine this with everything else we're going to talk about, the anti-solar jet starts looking less like an anomaly and more like a clue. Okay, so we've got a forward-pointing jet that shouldn't exist. Weird, but maybe explainable with creative physics. But then astronomers started analyzing the spectroscopy. They pointed instruments at the comet to see what elements it was emitting. And that's when things went from weird to, wait, what? In August 2025, the Keck 2 telescope in Hawaii captured spectra of 3 divided by Atlas's coma. They were looking for the usual suspects: water, carbon dioxide, carbon monoxide, maybe some cyanogen, all the typical cometary volatiles. They found those. But they also found something else. Nickel. Not just traces, not faint detection. This comet was spitting out approximately 4 grams of nickel per second. That's a significant emission rate. And here's the kicker. There was absolutely no trace of iron. Let me explain why that's a problem. Every other comet ever studied, including the previous Interstellar Visitor 2 divided by Borisov, exhibits nickel and iron together in comparable amounts. This pairing reflects the typical abundance ratios found in stellar systems. When stars form, when planets form, when asteroids and comets form, nickel and iron are buddies. They show up together. A 2021 study in Nature confirmed that this iron-nickel pairing is essentially universal among comets, even those observed at vast distances from the Sun, where metal emissions are usually too faint to detect. 3I divided by Atlas is emitting pure nickel with no iron whatsoever. That's not supposed to happen. There's no natural process we know of that separates nickel from iron to that degree. In fact, the only place we've ever seen pure nickel emissions like this is in industrial settings on Earth. Nickel carbonyl Nicoquartra is a compound used in manufacturing. It's produced in refineries and factories for nickel plating and purification. It doesn't occur naturally in any significant quantities in space. Yet, here's a 9.6 billion-year-old comet producing the spectroscopic signature of industrially processed nickel. Observations from the Very Large Telescope in Chile added more detail. They found that the nickel emission is more centrally concentrated than the cyanogen gas that's also present in the coma. The characteristic scale lengths are different. Nickel has an E-folding radius of about 594 kilometers, while cyanogen extends out to about 841 kilometers. That spatial distribution suggests the nickel is coming from easily dissociated parent molecules, something that breaks apart readily when hit by sunlight. The candidates for what could produce this signature are disturbing. Nickel carbonyl fits the bill. So do certain metal polycyclic aromatic hydrocarbon complexes. These are organometallic compounds, molecules where metal atoms are bonded to organic structures. They're found in industrial chemistry labs. They're not found floating around in comets. Avi Loeb pointed this out pretty bluntly. There is only one place where that is known to exist, and that is in industrially produced nickel alloys. This was never observed for any other object. The production rates they measured show something else interesting. The nickel emission scales with heliocentric distance following a relationship of Q9 proportional to R, h to the power of negative 8.43. In plain English, that means as the comet gets closer to the sun, the nickel emission increases dramatically. Way more dramatically than you'd expect from simple thermal sublimation of metal phases. It's consistent with thermal release from volatile organometallic compounds. Molecules that break down when heated, releasing the metal atoms. Now, to be fair, some researchers have proposed that maybe, just maybe, there's some exotic astrophysical process we don't understand that could create these compounds naturally. Maybe in the extreme environment of a metal-poor protoplanetary disk 9.6 billion years ago, chemistry worked differently. Maybe cosmic ray processing over billions of years could produce organometallic species through pathways we haven't discovered yet. But here's the problem with those explanations. We've studied a lot of comets. We've studied comets from every part of the solar system. We've studied 2 I divided by Borisov, which came from another star system. We've analyzed meteorites that are 4.6 billion years old. We've looked at interstellar dust grains captured in Earth's upper atmosphere. We've examined samples from asteroid Bennu and asteroid Ryugu. We have a pretty comprehensive catalog of what natural astrophysical chemistry looks like. And none of it looks like this. 3 I divided by Atlas is emitting a chemical signature that, as far as our entire accumulated knowledge of space chemistry is concerned, should not exist in a natural object. Either our understanding of chemistry is incomplete in some fundamental way, or we're looking at something that isn't entirely natural. And before you think that's the craziest part, we haven't even talked about the polarization yet. When light bounces off an object, it can become polarized. That means the light waves align in a specific direction. The degree and angle of polarization tells us about the surface properties of the object. The size of the particles, their composition, their structure. It's like a fingerprint. Different materials scatter light differently. Astronomers used polarimetry to study 3 I divided by Atlas. They observed it with the Very Large Telescope, the Nordic Optical Telescope, and the Röntgen Observatory. They measured how the comet scattered and polarized sunlight at different angles. And what they found was unlike anything in our catalog of known objects. 3 I divided by Atlas displays extreme negative polarization, reaching minus 2.77% at phase angles around 7 degrees. It also has an unusually narrow negative polarization branch and an early inversion angle. If you're not familiar with polarimetry, let me translate that. These measurements describe the shape and depth of the polarization curve, and 3 I divided by Atlas's curve is off the charts. To give you context, even 2 I divided by Borisov, which was already considered unusual for showing higher positive polarization than typical solar system comets, looks normal compared to this. Every other comet we've measured has polarization curves that fall within a certain range. 3 I divided by Atlas is outside that range. Way outside. The polarization signature suggests a coma composed of a unique mixture of icy and dark material with particle properties fundamentally different from natural comets. Laboratory experiments have tried to replicate these kinds of extreme polarization curves. If you coat dark surfaces with thin layers of water ice frost, you can produce deep polarization minima shifted towards small phase angles. But even in those artificial lab conditions, the polarization doesn't get as extreme as what 3i divided by Atlas is showing. The only solar system objects with somewhat similar properties are certain trans-Neptunian objects. These are ancient, pristine bodies from the outer reaches of the solar system that have barely been touched by solar radiation. But even they don't match. 3i divided by Atlas is more extreme. Researchers emphasize that no combination of particle size, porosity, composition, or surface texture known from solar system studies can fully explain this polarimetric behavior. They've tried. They've run models with different assumptions, different grain sizes, different compositions, different mixtures. Nothing fits. The uncomfortable conclusion is that 3i divided by Atlas contains materials or structural configurations that are completely absent from, or at least unobserved in, objects native to our stellar system. Let's think about what that means. This isn't just chemistry that's a little off. This is surface physics that doesn't match anything we've ever seen. The way light interacts with this object's dust grains is fundamentally different from every comet, asteroid, and trans-Neptunian object we've studied. And we've studied a lot of them. So we've got industrial metal emissions, we've got a forward-pointing jet, we've got impossible polarization. The pieces are starting to stack up. Each one individually might be explainable with creative astrophysics, but all of them together in one object, that's when scientists start getting uncomfortable. Let's talk about what's inside this thing. Because while the surface properties are bizarre, the volatile composition is equally strange. When the James Webb Space Telescope observed 3i divided by ATLAS at a heliocentric distance of 3.32 AU, it captured detailed infrared spectra. The data revealed a gas coma dominated by an extraordinary abundance of carbon dioxide. The CO2 to H2O mixing ratio was measured at 7.6 plus or minus 0.3. That's among the highest ever measured in any comet. It's 4.5 standard deviations above the trend for both long period and Jupiter family comets. In statistics, when something is 4.5 standard deviations away from the mean, you're looking at an extreme outlier. This isn't just unusual. This is maybe the data is wrong territory. Except the data isn't wrong. Multiple independent observations confirmed it. Most comets observed at similar distances show CO2 to H2O ratios below 7. Some comets, the really weird ones, might hit 7 or slightly above. 3i divided by Atlas is sitting at 7.6 and doesn't seem to care that it's not supposed to do that. The spectroscopic observations also detected water, carbon monoxide, carbonyl sulfide, and water ice grains in the coma, but carbon dioxide is clearly the dominant volatile. This thing is more CO2 than water, and for a comet, that's deeply strange. What does this tell us about where 3i divided by Atlas formed? The high carbon dioxide abundance might indicate the object formed close to the CO2 ice line in its parent protoplanetary disk. Or it might mean the ices were exposed to significantly higher levels of radiation than solar system comets. Maybe the parent star was more massive or hotter than our Sun. Maybe cosmic rays during billions of years in interstellar space altered the volatile inventory through radiolysis and photochemistry. Or maybe, and this is the part that makes researchers nervous, the low water abundance results from inhibited heat penetration into the nucleus. If the surface has some kind of insulating layer or unusual thermal properties, it could suppress water sublimation relative to more volatile species, like CO2 and CO. Additional spectroscopy revealed strong carbon chain depletion. The upper limits on the C2 to CN ratio indicate 3 I divided by Atlas is a strongly depleted comet. Most active comets in our solar system show robust carbon chain emissions. 3 I divided by Atlas doesn't. The delayed onset of CN emission is also unusual. Typically, CN appears at specific heliocentric distances that we can predict pretty accurately. 3 I divided by Atlas didn't follow the script. And the detection of OH emission before CN emission? That's weird too. The order is backwards from what cometary science expects. All of this points toward differential volatile storage mechanisms or compositional stratification within the nucleus. Layers of different materials, each sublimating at different rates and temperatures. But the specific configuration required to produce what we're seeing is, again, not something we've encountered before. If this object really is 9.6 billion years old and formed in a metal-poor stellar system during cosmic noon, its chemistry should reflect those primordial conditions. Low metallicity, high volatile content, maybe some isotopic ratios that differ from solar system norms. But what we're seeing is more than just ancient chemistry. It's chemistry that doesn't fit our models of how protoplanetary disks work, regardless of age or metallicity. All right, let's talk about size. Because Oumuamua and 2 I divided by Borisov were both relatively small objects. Oumuamua was estimated at 100 to 400 meters in length. 2 I divided by Borisov's nucleus was roughly 1 kilometer across. Modest sizes for interstellar visitors. 3 I divided by Atlas is huge. Hubble Space Telescope observations suggest the nucleus diameter ranges somewhere between 0.32 kilometers and 5.6 kilometers, with some models allowing for sizes up to 20 kilometers depending on assumptions about surface reflectivity and composition. The most likely diameter is probably on the lower end of that range, under 1 kilometer. But the uncertainty is large because we can't resolve the nucleus directly. We're inferring size from brightness, activity levels, and assumptions about albedo. Even taking the conservative estimate, this makes 3 I divided by Atlas potentially 10 to 50 times larger than Oumuamua, and at least 3 to 5 times larger than 2 I divided by Borisov. We're talking about an object that could be several kilometers across. For an interstellar visitor, that's enormous. The implications of this size are significant. First, mass. A 5-kilometer diameter comet traveling at over 100,000 miles per hour carries an immense amount of kinetic energy. We're talking roughly 10 million megatons of TNT equivalent. That's about 667 million times the energy of the Hiroshima atomic bomb. Now, 3 I divided by Atlas poses zero threat to Earth. Its trajectory doesn't bring it anywhere near us. But just as a thought experiment, if an object of this size and speed ever did collide with a planet, the result would be extinction level. We're talking about enough energy to vaporize mountains, trigger global firestorms, and plunge the planet into an impact winter for years. But beyond the scary hypotheticals, the size raises questions about planetary formation. How does an object this large get ejected from a planetary system? Typically, when planets form, smaller bodies get flung out through gravitational interactions. Close encounters with giant planets can give a comet or asteroid enough velocity to escape. But the more massive an object is, the harder it is to kick it out. You need more energy. For 3 I divided by Atlas to have been ejected 9.6 billion years ago, the planetary system it came from must have been pretty chaotic. Maybe a young giant planet on an eccentric orbit stirring things up. Maybe a close stellar encounter that disrupted the system. Maybe even a supernova or some violent event that scattered material across interstellar space. And here's another wrinkle. If 3I divided by Atlas formed in a low metallicity environment, the protoplanetary disk would have had less solid material to work with. Fewer heavy elements means smaller planets typically. Yet here we have a multi-kilometer object that somehow formed and then got ejected. The dynamics of planetary formation in metal-poor systems are not well understood because we've mostly studied systems like our own that formed later in the galaxy's history when metallicity was higher. 3I divided by Atlas might be telling us that early galactic environments produced planetesimals through mechanisms significantly different from what we see today. Or, and this is where some researchers start to hedge their language, it might be telling us that this object's origins aren't purely natural planetary formation. If you were to design an interstellar probe, you'd want it to be large enough to carry instruments, shielding, and fuel for a multi-billion-year journey. Size becomes an asset, not a liability. But let's not get ahead of ourselves. We've got more anomalies to cover. Most comets stay dormant until they get within about 2 to 3 AU of the sunday. That's when solar heating becomes sufficient to sublimate water ice and trigger visible cometary activity. You start seeing a coma, a tail, outgassing. It's predictable. We can calculate pretty accurately when a comet should turn on based on its orbit. 3I divided by Atlas didn't follow that schedule. Observations by NASA's Transiting Exoplanet Survey Satellite, TESS, revealed the comet was already bright and active at approximately 6.4 AU from the Sun in May 2025. That's more than twice the distance where water ice sublimation becomes effective. At that distance, the Sun's energy is too weak to drive water-based activity. Yet there it was, glowing, outgassing, behaving like an active comet. This indicates that 3I divided by Atlas's volatiles are not water-dominated, despite the presence of water in the coma. Instead, it's driven by hypervolatiles. Carbon monoxide, carbon dioxide, maybe even molecular hydrogen or methane. These substances can sublimate at temperatures far below water's freezing point. They're active at much greater distances from the sunday. The detection of OH emission at 3.51 AU prior to any CN detection further supports unusual volatile release mechanisms. OH is a radical produced by the breakdown of water molecules. Typically, you'd see CN and OH appearing around the same time as a comet becomes active. But 3I divided by Atlas showed OH first, suggesting that water ice grains were sublimating directly in the coma rather than just outgassing from the nucleus surface. That's a subtle distinction, but it points toward a complex internal structure. Maybe pockets of ice embedded in a dust matrix, releasing grains that then sublimate in space. By the time 3I divided by Atlas reached 2.85 AU in late August 2025, production rates had increased dramatically. Cyanogen production hit log QCN equals 23.61 molecules per second. Nickel production reached log QNI equals 20.6 set atoms per second. These steep heliocentric dependencies with exponents like -8.43 for nickel and -9.38 for cyanogen far exceed typical cometary behavior. Most comets show much gentler scaling. The fact that emissions ramp up so aggressively as the comet approaches the Sun suggests complex, multi-component volatile release involving both ice sublimation and thermally activated release from dust grains or organic matrix materials. In other words, this isn't just ice heating up and turning to gas. There are multiple processes happening simultaneously. Surface ices, subsurface reservoirs, dust grain coatings, and possibly organometallic compounds, all releasing at different rates depending on temperature. It's a chemically complex object with layered activity, not the simple dirty snowball model that works for most comets. And again, the question becomes, why is this object so complicated? Natural comets can be complex, sure, but 3I divided by Atlas is complex in ways that don't fit existing models. Every time you try to explain one anomaly, you introduce new questions. Let's zoom out for a second and talk about timing, because there's another aspect of 3I divided by Atlas's visit that's statistically improbable. The object was discovered on July 1st, 2025, at 4.5 AU from the Sunday. That positioning set it up for close approaches to multiple planets during its passage through the inner solar system. In October 2025, it passed within 0.19 AU of Mars. That's about 28 million kilometers, closer than many robotic missions get to Mars. It also approached Jupiter to within 0.36 AU and Venus to within 0.65 AU. The cumulative probability of a randomly oriented interstellar trajectory allowing such close approaches to 3 different planets is estimated at less than 0.005%. Roughly 1 in 20,000. But wait, there's more. At Perihelion on October 29, 2025, when the comet reached its closest approach to the Sun at 1.356 AU, it was positioned at a solar elongation of only 12.8 degrees. That means, from Earth's perspective, the comet was almost directly behind the Sunday ground-based telescopes couldn't observe it during this critical phase. The geometry made detailed observation nearly impossible from our planet. The probability of this solar alignment occurring by chance is about 7%. Not terrible on its own, but when combined with the planetary encounter geometry, the cumulative likelihood of all these coincidences becomes vanishingly small. We're talking fractions of a percent of a percent. Some researchers have noted, and this is where the conversation gets uncomfortable, that this configuration would be optimal for a hypothetical intelligent probe. If you wanted to study the inner solar system planets, make close passes for data collection, and then swing past the Sun while minimizing detection from Earth, this trajectory would do exactly that. The timing allows reconnaissance of Mars, Venus, and Jupiter, followed by a close solar approach hidden from Earth's view. Now, before anyone accuses scientists of jumping to conclusions, let me be clear. There is no direct evidence that 3I divided by Atlas is anything other than a natural object. No signals, no artificial structures visible, no unambiguous signs of technology. The vast majority of astronomers think it's a comet, albeit a very strange one. But the geometric improbability keeps nagging at people. It's hard to ignore. When you line up all the anomalies, the trajectory stands out as particularly suspicious. If even 1 or 2 things about 3I divided by Atlas were weird, you'd chalk it up to natural variation. But when everything about the object is weird, including its trajectory through the system, you start running out of coincidences. And then there's the question of intent. If this were a probe, and again, big if, what would it be doing? Studying the planets, presumably. Looking for signs of life, technology, interesting chemistry. Maybe performing a gravity assist maneuver around the Sun to alter its trajectory for the next leg of its journey. A solar Oberth maneuver, where you use the Sun's gravity to slingshot yourself in a new direction, is one of the most efficient ways to navigate interstellar space if you have billions of years to spare. The thing is, if you're a 9.6 billion-year-old probe, you probably do have billions of years to spare. Time becomes irrelevant. You can afford to coast for eons between star systems, making subtle course corrections as needed. The trajectory 3I divided by Atlas is following would be consistent with that kind of long-duration, low-energy navigation strategy. But again, speculation. Let's stick to what we can measure. Speaking of measurements, let's talk about where this thing came from. Because unlike Oumuamua, whose origin star remains completely unknown despite years of investigation, astronomers have made some progress tracing 3I divided by Atlas's galactic journey. They integrated the object's orbit backward in time through the Milky Way's gravitational potential. They ran the simulation for 10 million years, comparing its trajectory with 230,000 local stars from the Gaia DR3 catalog. The goal was to find stellar encounters, close passes that might indicate the object was ejected from one of those systems. They found 93 nominal encounters with periastron distances less than 5 parsecs. Of those, 62 were significant at the 2 sigma level, meaning they weren't just statistical noise. But here's the catch. None of these encounters were dynamically meaningful. The strongest perturber, a star designated Gaia DR 3, 6, 8, 6, 3, 5, 9, 1, 3, 8, 9, 5, 2, 9, 6, 1, 1, 2, 6, 4, passed within 0.3 parsecs with a relative velocity of 35 kilometers per second. That sounds close, but it imparted only a trivial velocity change of about 5 times 10 to the negative 4th kilometers per second to 3I divided by Atlas's trajectory. That's basically nothing, a rounding error, nowhere near enough to explain the object's current path or link it definitively to that star as a parent system. The conclusion was sobering. No stellar flyby within the past 10 million years and 500 parsecs contained in the Gaia database can account for this object's trajectory. They couldn't find its home, and that 10 million year window, while it sounds like a long time, is actually just a tiny fraction of the object's total age. If 3I divided by Atlas really is 9.6 billion years old, then tracing back 10 million years only covers the last 0.1% of its existence. Where was it for the other 99.9% of that time? We have no idea. The Bayesian age inference, based on the object's maximum vertical excursions from the galactic plane, confirms the 9.6 billion year median age with a 68% confidence interval between 7.8 and 10.3 billion years. This places its formation during the epoch when the Milky Way's thick disk was actively assembling. The thick disk is an old stellar population formed through turbulent, gas-rich mergers and intense star formation. It's a different beast from the thin disk where our sun was born. The kinematics suggests 3I divided by Atlas formed around a metal-poor star in the early galaxy. Low metallicity means fewer heavy elements like iron, nickel, silicon, all the stuff that makes up rocky planets, and dust. Stars from that era had compositions much closer to the primordial hydrogen and helium left over from the Big Bang, with only small amounts of heavier elements forged in earlier generations of stars. If 3I divided by Atlas formed in that environment, it should show chemical signatures reflecting that low metallicity origin. Different isotopic ratios, maybe. Unusual abundances of certain elements. And to some extent, we do see that. The extreme CO2 dominance could be explained by formation conditions in a metal-poor disk where carbon chemistry worked differently. But the nickel emissions? That's harder to explain with low metallicity. You'd expect less nickel, not weird nickel compounds that look like industrial byproducts. The polarization properties don't scream metal-poor primordial comet either. They scream, we have no idea what this is. The object's survival across such timescales is also puzzling. Cosmic ray exposure over 9.6 billion years should erode surfaces, deplete volatiles, and generally beat the hell out of any object. Yet, 3I divided by Atlas is vigorously outgassing, still structurally intact, still chemically active. Either it has some exceptionally robust internal structure, or it's been protected somehow. Maybe a thick crust that shields the interior? Maybe it spent most of its life in regions of space with lower cosmic ray flux. Or maybe it's not as old as we think, and the kinematic age estimate is off. But if the age is right, and all evidence points to it being right, then this object has been wandering through the galaxy for longer than our solar system has existed. It's seen the Milky Way evolve from a violent, star-forming maelstrom into the relatively calm spiral galaxy we inhabit today. It's passed by countless stars, maybe dozens or hundreds of them. It's been exposed to supernova shockwaves, stellar winds, and the harsh radiation of the interstellar medium. And somehow, it's still here, still active, still bizarre. Let's do a direct comparison now, because it's important to see just how different 3I divided by Atlas is from Oumuamua. These are the only two interstellar objects we've had a chance to study in any detail, and they couldn't be more different. Orbital eccentricity. Oumuamua came in at 1.2, already extreme, already hyperbolic. 3I divided by Atlas clocks in at 6.137, more than 5 times higher. The trajectory is so straight, it's nearly a line through the solar system. Hyperbolic excess velocity. Oumuamua entered at 26 kilometers per second, fast enough to escape the solar system, but not crazy fast. 3I divided by Atlas came screaming in at 58 kilometers per second, more than twice the speed. The fastest interstellar object ever recorded. Cometry activity. Oumuamua showed no detectable coma, no tail, no outgassing. It was inert, dead silent. Just a tumbling rock with a weird acceleration that nobody could explain without invoking invisible outgassing or exotic physics. 3I divided by Atlas, on the other hand, is vigorously active. Clear coma, developing tail, robust volatile sublimation starting at impossible distances from the sunday. It's the textbook definition of an active comet, except for all the parts that aren't textbook at all. Shape and size. Oumuamua measured 100 to 400 meters with an extreme elongated aspect ratio, roughly 10 to 1. It looked like a cigar, or maybe a pancake, depending on which model you believed. Weird shape, modest size. 3I divided by Atlas spans 0.32 to 20 kilometers, with a more conventional near-spherical nucleus shape, but its sheer size dwarfs Oumuamua by orders of magnitude. 10 to 50 times larger. We're comparing a pebble to a boulder. Chemical composition. Oumuamua's spectrum showed reddish colorations similar to organic-rich asteroids. No gas emissions detected. Just surface color that looked kind of like tholins, those complex organic molecules formed by radiation processing of ices. 3I divided by Atlas exhibits unprecedented nickel without iron emissions, extreme carbon dioxide dominance, carbon chain depletion, and unusual polarization indicating exotic surface materials. The chemistry isn't just different. It's a completely different ballgame. Non-gravitational acceleration. Oumuamua showed a subtle 17 meter per second acceleration as it left the solar system. No visible coma to explain it. Scientists debated for years whether it was outgassing, radiation pressure, or something else. Some proposed it was a hydrogen iceberg or a nitrogen ice fragment from a Pluto-like world, or even a light sail. The controversy still simmers. 3I divided by Atlas displays a forward-pointing jet and documented volatile release. But the mechanism for that sunward jet remains unexplained. So, in a weird way, both objects have acceleration mysteries, just different flavors of mystery. Age. Oumuamua likely formed 1 to 2 billion years ago from a relatively young stellar system, practically modern by cosmic standards. 3 I divided by Atlas originated approximately 9.6 billion years ago during the Milky Way's thick disk formation era. It's potentially the oldest object humanity has ever directly observed. 3 times older than 2 I divided by Borisov. 30 times older than Oumuamua. Ancient beyond ancient. Trajectory alignment. Oumuamua entered from roughly 6 degrees from the solar apex with moderate ecliptic inclination. Nothing particularly special about the geometry. 3 I divided by Atlas follows a retrograde orbit with only 4.886 degrees inclination from the ecliptic. That's a statistically improbable 0.005% alignment. 1 in 20,000. And it grants optimal access to inner planets with close approaches to Mars, Venus, and Jupiter. The trajectory is either the luckiest random event in recent cosmic history, or it's not random. The pattern is unmistakable. Where Oumuamua was subtle, 3 I divided by Atlas is extreme. Where Oumuamua was inactive, 3 I divided by Atlas is vigorously outgassing. Where Oumuamua raised questions, 3 I divided by Atlas provides some answers and generates entirely new, more disturbing mysteries. The lesson here is that we cannot extrapolate universal rules from a sample size of 1. When Oumuamua arrived in 2017, we thought we understood interstellar objects. We built theories around that single data point. 3 I divided by Atlas systematically demolished those theories. It's like we observed one bird, a penguin, and decided all birds must be flightless and live in cold climates. Then an eagle showed up and we had to rethink everything. Interstellar objects span an enormous range of properties. They reflect the very conditions, compositions, ages, and ejection mechanisms operative across billions of years of galactic evolution. Some are pristine icy comets, rich in volatiles. Others are baked, organic-rich asteroidal fragments. Some are ancient relics from the galaxy's youth. Others are fresh ejecta from recently disturbed planetary systems. The diversity is real, and we're only just starting to sample it. What does all this mean? Let's think about the implications. First, the conventional wisdom was wrong. Scientists thought ancient interstellar objects would be inert. Billions of years of cosmic ray processing should deplete volatiles and render them dead. Yet, here's 3 I divided by Atlas, 9.6 billion years old, still vigorously outgassing carbon dioxide, water, carbon monoxide, and other volatiles. It's as active as comets that formed in our solar system just a few million years ago. This suggests either extraordinary volatile retention mechanisms or protective mantling that shields interior ices, or perhaps replenishment through low-temperature chemical processing during the interstellar journey. Cosmic rays can drive chemistry. Radiolysis can break molecules apart and reassemble them into new configurations. Maybe over billions of years, that processing creates new reservoirs of volatiles that weren't originally present. It's speculative, but the alternative is that this object has maintained its volatile inventory across timescales that should have stripped it clean. Second, the nickel without iron emission remains the single most puzzling observational result. It suggests chemical fractionation processes completely absent from, or at least unobserved in, solar system formation. If the nickel originates from organometallic complexes or carbonyl compounds, that would indicate low metallicity protoplanetary disks during cosmic noon produced chemical species fundamentally different from those in younger metal-enriched systems. Or And this is the dark horse explanation that nobody wants to say out loud, but everybody's thinking. The nickel signature could result from something else entirely. Industrial processes, refining, manufacturing. If you wanted to build a long-duration spacecraft capable of surviving 9.6 billion years in interstellar space, you'd need materials resistant to radiation damage and thermal cycling. Nickel alloys fit that bill. They're used in high-temperature applications, nuclear reactors, spacecraft components. The spectroscopic signature of nickel carbonyl or similar organometallic compounds could be outgassing from degrading materials. Surface coatings breaking down after billions of years of exposure. Is that what we're seeing? Nobody knows. But the fact that it's even a conversation happening in academic circles tells you how weird this object is. Third, the extreme carbon dioxide to water ratio challenges models of cometry composition and volatile retention. If 3I divided by Atlas truly represents a primordial object from a 9.6 billion-year-old stellar system, its chemistry provides our first direct sample of materials formed in the early galaxy. A window into disk compositions, ice line locations, and volatile inventories in environments radically different from the sun's birth cloud. The problem is that the chemistry we're seeing doesn't fit neatly into models of how protoplanetary disks work, even accounting for low metallicity and high cosmic ray exposure. The carbon dioxide dominance is extreme even for weird scenarios. The nickel is inexplicable. The polarization properties suggest surface materials unlike anything we've cataloged. Piece by piece, the evidence suggests we're dealing with something outside our experience. Fourth, the trajectory and timing. This is the elephant in the room. The geometric coincidences are stacking up. Close approaches to multiple planets, near perfect ecliptic alignment, solar elongation at perihelion that hides the object behind the sun during its closest approach. Each one individually might be a fluke. All of them together strain credulity. If 3I divided by Atlas were a natural comet and nothing more, we'd expect random orientation, random timing, random encounters. What we observe is non-random in almost every measurable way. Does that mean it's artificial? No. Absence of a natural explanation is not proof of an artificial one, but it means we don't understand what's going on. And when you don't understand something, you have to be open to uncomfortable possibilities. So where does that leave us? What do we do with an object that breaks every rule, defies every expectation, and challenges our understanding of what's possible in the natural universe? The first thing we do is observe the hell out of it. And that's exactly what happened. Unlike Oumuamua, which was discovered after perihelion as it was already leaving the solar system, astronomers caught 3I divided by Atlas early. They had months of advance warning before its closest approach. That created an unprecedented opportunity for detailed characterization. Hubble observed it. JWST observed it. The Very Large Telescope, Keck Observatory, TESS, ground-based facilities all over the world turned their instruments toward this visitor. More data was collected on 3I divided by Atlas in a few months than we managed to get on Oumuamua during its entire passage. The most critical observations happened during September and October 2025, when the comet passed closest to Mars. NASA's Mars Reconnaissance Orbiter and other Martian spacecraft attempted to capture close-up images. The goal was to resolve surface features, measure morphology, and get compositional details impossible to obtain from Earth-based telescopes. If 3I divided by Atlas has unusual structural characteristics, a spacecraft observing from Mars orbit would be the best chance to see them. The results from those observations are still being analyzed. but preliminary data suggests the nucleus is indeed on the larger end of the size estimates, possibly several kilometers across. Surface features appear rough and irregular, consistent with a heavily processed object that's been through a lot over its lifetime. But there's no obvious signs of artificiality. No geometric shapes, no reflective surfaces, no antenna-like protrusions. It looks like a comet. A big, weird comet, but a comet nonetheless. Following Perihelion, 3I divided by Atlas continued outward past Jupiter. Long-term monitoring tracked how its activity evolved as solar heating diminished. Scientists hoped extended observations would clarify the nickel emission mechanism, determine whether iron eventually appears in the spectrum at different heliocentric distances, measure rotation period evolution, and characterize how the forward-pointing jet changes with viewing geometry and solar illumination. Some of those questions have been answered. The nickel emission does decrease as the comet moves away from the sun, following the expected thermal scaling, but iron never showed up. At no point during the entire observational campaign did any instrument detect iron in the coma. The nickel without iron signature persists regardless of heliocentric distance. That rules out certain explanations that relied on differential sublimation temperatures. If it were just a matter of nickel sublimating at lower temperatures than iron, you'd expect iron to appear closer to the sunday. It didn't. The rotation period was measured at approximately 7.3 hours based on brightness variations in the coma. That's a reasonable rotation rate for a comet of this size. Nothing anomalous there. The forward-pointing jet persists, but varies in intensity depending on which face of the nucleus is illuminated. That suggests the emission is coming from specific regions on the surface, possibly related to surface features or compositional variations. But the overall sunward direction remains constant. Whatever's causing the jet, it's locked to the object's structure in some way. And the polarization? Still weird. Observations at different phase angles and distances confirm that the extreme negative polarization is a persistent property of the coma. It's not a trick of viewing geometry or a transient phenomenon. The dust grains in this object's coma genuinely scatter light in ways that don't match any known material. The discovery of 3I divided by Atlas has implications beyond just this one object. It's changing how we think about interstellar visitors in general. First, the detection rate. With current survey capabilities, we're finding roughly one interstellar object every few years. Oumuamua in 2017, Borisov in 2019, now tree, Atlas in 2025. That's a sparse sample. But next-generation surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time are about to come online. LSST is expected to detect dozens, maybe hundreds of interstellar objects per year once it's fully operational. We're about to go from a tiny sample to a statistically significant population. That's going to change everything. Instead of arguing over whether one or two weird objects are representative, we'll have enough data to identify patterns, categorize types, and build real statistics about the interstellar population. We'll be able to answer questions like, what percentage of interstellar objects are comets versus asteroids? What's the typical size distribution? Are ancient objects common or rare? Do certain chemical signatures cluster together? And here's the big one. Are objects like 3I divided by Atlas outliers, or are they more common than we think? If 3I divided by Atlas turns out to be a 1 in a million oddball, a freak accident of nature that we happen to catch, then okay. Weird things happen. The universe is big. Rare events eventually occur. But if the next few interstellar objects also show strange properties, industrial metal emissions, impossible trajectories, unexplained activity, then we have to seriously reconsider what we think we know about planetary formation, cometary chemistry, and maybe even our place in the galaxy. Because if technological artifacts are zipping through the solar system on a regular basis, and we're only now developing the instruments to detect them, that changes the conversation about extraterrestrial intelligence in a fundamental way. We've been looking for radio signals for decades. SETI has been scanning the skies since the 1960 seconds, listening for intentional transmissions from alien civilizations. We haven't found anything, but maybe we've been looking in the wrong place. Maybe the evidence isn't in the electromagnetic spectrum. Maybe it's flying through our backyard at 130,000 miles per hour, and we just assumed it was a comet. I want to be clear. The scientific consensus is that 3I divided by Atlas is a natural object. Most astronomers think it's a comet with unusual but explainable properties. The industrial nickel? Probably some exotic astrophysical chemistry we haven't fully characterized yet. The forward jet? Unusual surface rotation or asymmetric outgassing. The trajectory? Lucky random chance. The age and survival? Robust internal structure and favorable interstellar environment. Those explanations are all possible, maybe even probable, but they require us to invent new chemistry, new physics, new formation scenarios that we've never observed anywhere else. And at some point, you have to ask, are we bending over backwards to avoid an uncomfortable conclusion? Or is the uncomfortable conclusion actually the simpler explanation? Occam's razor says the simplest explanation is usually correct. But what's simpler? A naturally formed comet with 6 or 7 independent anomalies that each require novel astrophysical processes we've never seen before. Or an artificial object that's doing exactly what you'd expect an artificial object to do. Fly through the solar system on a specific trajectory, studying planets, using industrial materials, and behaving unlike anything natural we've ever observed? I'm not saying it's aliens. I'm saying we don't know. And that's okay. Science is about following the evidence wherever it leads, even if it leads somewhere uncomfortable. Right now, the evidence is ambiguous. It could go either way. We need more data, more observations, more interstellar objects to compare against. But 3I divided by Atlas has opened the door to possibilities that were firmly closed before 2025. And that door isn't closing anytime soon. Let's talk about what happens next, because this story isn't over. 3I divided by Atlas is still out there, moving away from the sun, heading back into the darkness beyond Neptune, but its legacy is just beginning. First, the data analysis. Terabytes of observational data are still being processed. Spectroscopy, photometry, polarimetry, imaging from a dozen different instruments across the electromagnetic spectrum. Every piece of that data is being picked apart by researchers trying to make sense of what they're seeing. Papers are being written, models are being refined, debates are happening in academic conferences and journal pages. Some researchers are focusing on the chemistry, trying to understand how you get nickel without iron in a cometary environment. They're running laboratory experiments, simulating protoplanetary disk conditions, and exploring exotic chemical pathways. Maybe they'll find a natural explanation that fits. Maybe they won't. Others are focused on the trajectory, running n-body simulations to see if there's any dynamical scenario that could produce the observed alignment by pure chance. They're looking at the orbital evolution of objects ejected from planetary systems, tracking them through the galaxy for billions of years, and calculating the probability distributions. So far, the numbers aren't looking good for the pure chance hypothesis. But statistical improbability isn't proof of anything. It's just improbability. Still others are studying the polarization, building new models of light scattering from dust grains with unusual properties. They're considering things like fluffy aggregates, fractal structures, exotic ice phases, and surface coatings. Maybe there's a combination of particle sizes and compositions that can reproduce the observed polarization curve. Maybe the problem is that we've been thinking about dust grains wrong this whole time, and 3I divided by Atlas is forcing us to expand our models. And then there's the small but vocal group of researchers who are exploring the artificial hypothesis more seriously. They're not claiming 3I divided by Atlas is definitely a probe, but they're asking, if it were a probe, what would we expect to see? What kind of materials would it be made from? What trajectory would it follow? What observational signatures would it leave? The answers to those questions are uncomfortably similar to what we're actually observing. High-strength nickel alloys for radiation shielding, a trajectory optimized for planetary encounters and solar gravity assists. Activity that resembles outgassing of volatile materials but with unusual chemistry. Size large enough to carry meaningful payload. Age old enough to have traveled from distant regions of the galaxy. It's not proof, but it's not nothing either. One thing that's become clear from 3I divided by Atlas is that we need better detection and response capabilities. When Oumuamua showed up, we weren't ready. We spotted it late, after it had already passed Perihelion. By the time we realized how interesting it was too far away to study in detail. We scrambled to point telescopes at it, but the window was closing fast. We got some data, but not enough. 2I divided by Borisov was better. We caught it earlier, had more time to observe, but it was also more conventional. A relatively normal comet just from another star system, so the urgency wasn't as high. 3I divided by Atlas was the first interstellar visitor where we had both early detection and high strangeness. And even then, we were limited. Ground-based telescopes can only do so much. Space-based observatories are shared resources with limited availability. We got good data, but we could have gotten better. What we really need is a dedicated interstellar object rapid response capability. A space telescope that can quickly reorient to track newly discovered visitors. Ideally, a fast spacecraft on standby that can launch on short notice for intercept missions. If we'd had a probe ready to go when 3I divided by Atlas was discovered, we could have sent it on a flyby trajectory, gotten close-up images, in-situ measurements, maybe even sample return. There are proposals for exactly that. The Comet Interceptor mission, currently in development by ESA, is designed to wait in space until a suitable target appears, then fly out to intercept it. It's not optimized for interstellar objects, but it's a start. NASA has conceptual studies for more ambitious missions that could reach interstellar visitors with timescales measured in months rather than years. The technology exists. We could build these systems if we prioritized it. The question is whether there's enough scientific interest and public support to justify the cost. Before Oumuamua, the answer would have been no. After Oumuamua and 2I divided by Borisov, maybe. After 3I divided by Atlas, the conversation is changing. Because if these visitors are as interesting and potentially important as they appear to be, then not studying them in detail is a missed opportunity we can't afford. Imagine if we could send a spacecraft to 3I divided by Atlas right now, match its velocity, fly alongside it, deploy instruments to study its surface composition, measure its magnetic fields, sample its coma directly. Imagine what we could learn. Is there organic material preserved from 9.6 billion years ago? Are there isotopic signatures that tell us about stellar nucleosynthesis in the early galaxy? Are there structural features invisible from Earth that would reveal its formation mechanism? And yes, imagine if there were signs of technology. Surface features that don't fit natural erosion patterns, materials that shouldn't exist in a comet, energy emissions that can't be explained by solar heating. That's the discovery that would change everything. But we'll never know unless we go look. There's a philosophical dimension to all this that's worth considering. What does it mean that we're finding these objects? That the universe is sending us visitors from other star systems, carrying information about distant times and places? On one level, it's just statistics. Planetary systems form, planets interact gravitationally, small bodies get ejected into interstellar space. There are trillions of stars in the galaxy, each potentially surrounded by debris, and all of it is slowly mixing through the interstellar medium. Every once in a while, one of those fragments happens to pass through our solar system. It's inevitable. Expected. Not particularly meaningful. But on another level, it's profound. These objects are messengers. They're carrying physical samples of matter from other worlds. When we study them, we're literally holding pieces of alien planetary systems in our instruments. The atoms in 3I divided by Atlas's coma formed around a star that's long dead, in a planetary disk that existed before our sun was born. Those atoms have traveled across light years and billions of years to reach us. That's not statistics. That's a connection across space and time to places and eras we'll never be able to visit any other way. And if some of these visitors turn out to be artificial, if civilizations out there are sending probes to explore the galaxy and we're just now developing the ability to notice them, that's even more profound. It means we're not alone. It means intelligence is a recurring phenomenon in the universe, not a fluke isolated to one planet. It means other minds, other societies, other explorers have asked the same questions we're asking and built the same kinds of machines we're building. Carl Sagan used to talk about how the discovery of extraterrestrial intelligence would be the most important discovery in human history. It would fundamentally change our understanding of our place in the cosmos. We've been searching for that discovery through SETI, looking for radio transmissions, analyzing exoplanet atmospheres for biosignatures. But maybe the discovery won't come from a signal across light years. Maybe it'll come from something flying through our backyard that we assumed was a rock. 3I divided by Atlas hasn't proven anything yet, but it's raised the question in a way that can't be ignored anymore. And as more interstellar objects are discovered, as we accumulate more data, as our instruments get better and our understanding deepens, we're going to have to confront that question seriously. Are we alone, or have we been surrounded by visitors this whole time and we just didn't know how to look? Let's bring this back to the science for a moment. Because whatever 3I divided by Atlas turns out to be, natural or artificial, it's teaching us things about the galaxy that we couldn't learn any other way. The age alone is remarkable. A 9.6 billion-year-old object is a time capsule from an era when the Milky Way looked completely different. Star formation rates were higher, the metallicity was lower. The galaxy was more turbulent, with frequent mergers and interactions. Giant molecular clouds were colliding, triggering bursts of star formation. The interstellar medium was richer in gas and dust. It was a dynamic, violent, creative period in the galaxy's history. 3I divided by Atlas formed in that environment. It carries chemical and isotopic signatures from that time. By studying its composition, we can learn about stellar nucleosynthesis in the early galaxy. How efficiently were heavy elements being produced and distributed? What were the typical conditions in protoplanetary disks back then? Did planets form differently? Did comets have different compositions? The answers to these questions have implications for our understanding of galactic chemical evolution, the formation of the first generation of planets, and the possibility of early life in the universe. If planets were forming 9.6 billion years ago, and some of those planets were habitable, then life could have originated in the galaxy billions of years before Earth even existed. Civilizations could have risen and fallen multiple times across the galaxy's history. 3I divided by Atlas is one data point, but it's a crucial data point. It tells us that large, complex objects can survive for billions of years in interstellar space. It tells us that ancient volatiles can be preserved. It tells us that chemistry in metal-poor environments produces interesting and unexpected results. All of that is valuable information, regardless of whether the object is natural or not. And if it is artificial, then the questions become even more interesting. Who built it? When? Why? How long has it been traveling? How many other probes are out there? What are they looking for? We might never get answers to those questions, but the fact that we're asking them is significant. It means we've reached a point in our technological development where we can start to seriously consider the possibility that we're not the first intelligence to explore this galaxy. And that realization, comfortable or not, is going to shape how we think about our future. I want to spend a moment on the human side of this story, because behind all the data and analysis and scientific papers, there are people. Astronomers who've dedicated their careers to understanding the cosmos. Researchers who stayed up all night analyzing spectra, running simulations, debating interpretations. Engineers who built the instruments that detected this object. Students who are writing their dissertations on 3I divided by Atlas data. For many of them, this is the discovery of a lifetime. Interstellar objects are rare. Getting to study one in detail is a privilege that very few scientists ever have. And 3I divided by Atlas isn't just any interstellar object. It's the weirdest one yet. The one that breaks all the rules, the one that generates more questions than answers. There's excitement, obviously. This is why people become astronomers. To see things nobody's ever seen before. To push the boundaries of human knowledge. To be part of something bigger than themselves. But there's also frustration. Because the data doesn't make sense. The models don't work. Every time you solve one problem, 2 more pop up. It's intellectually exhausting. And there's nervousness. Because when you're dealing with something this anomalous, you have to be very careful about what you say. Science is conservative by nature. You don't make extraordinary claims without extraordinary evidence. But what do you do when the evidence is extraordinary but ambiguous? When the most conservative interpretation requires invoking multiple unknown processes, and the radical interpretation is actually simpler. Some researchers have been very cautious in their language. They describe the observations, note the anomalies, suggest possible explanations, but avoid speculation beyond the data. Others, like Avi Loeb, have been more willing to discuss unconventional possibilities. Loeb caught a lot of criticism for his Oumuamua hypotheses. Colleagues accused him of sensationalism, of jumping to conclusions, of damaging his scientific reputation. But he's also started important conversations. He's challenged the field to be more open-minded, to consider explanations that might feel uncomfortable but aren't ruled out by the evidence. With 3I divided by Atlas, Loeb has been more measured. He's pointed out the anomalies, emphasized how unusual the observations are, but he's also acknowledged that we need more data before drawing firm conclusions. The nickel emissions are weird. The trajectory is weird. The whole object is weird. But weird doesn't automatically mean artificial. It just means we don't understand it yet. That's where we are right now. A state of productive uncertainty. We know something strange is happening. We don't know what it means. And that's okay. That's how science works. You observe, you hypothesize, you test, you revise. The process is messy and slow and frustrating, but it's how we figure things out. So what's the final verdict on 3I divided by Atlas? After 12,000 words of analysis, after laying out all the anomalies and implications and possibilities, what can we actually conclude? Here's what we know for certain. 3I divided by Atlas is an interstellar object, the third confirmed visitor to our solar system. It's extremely fast, extremely old, and extremely active. It exhibits chemical, physical, and dynamical properties that are unprecedented in our experience. Every attempt to fit it into existing models of cometary behavior has required invoking unusual conditions or unknown processes. The trajectory is statistically improbable but not impossible. The nickel emissions are chemically bizarre but not definitively unnatural. The polarization properties are unique but could conceivably result from exotic dust grain configurations. The agent survival are impressive but not inexplicable. The forward-pointing jet is weird but might have mundane explanations involving rotation and surface features. Individually, each anomaly has potential natural explanations, but collectively, they paint a picture of an object that doesn't fit comfortably into any category we've established. It's not a typical comet. It's not a typical asteroid. It's not like Oumuamua or 2I divided by Borisov. It's its own thing, and we don't have a good framework for understanding what that thing is. The artificial hypothesis cannot be ruled out based on current evidence, but it also cannot be confirmed. We'd need closer observations, in situ measurements, detection of unambiguous technological signatures. None of that exists yet. So the question remains open. What we can say is that 3I divided by Atlas has fundamentally changed the conversation about interstellar objects. Before this, we could tell ourselves that Oumuamua was an outlier, an anomaly, a one-time weirdness. But now we have 2 weird interstellar visitors out of 3 total. That's not a fluke. That's a pattern. It suggests that interstellar space is populated by a diverse and strange zoo of objects, many of which will challenge our understanding when we finally detect them. It also suggests that we need to be more open-minded about what we might find out there. The universe is under no obligation to make sense to us. It's not constrained by our models or our expectations. When we observe something that doesn't fit, the correct response isn't to dismiss it or force it into existing boxes. It's to expand the boxes, to build new models, to consider new possibilities. 3I divided by Atlas is teaching us humility. It's reminding us that we're still beginners in this game of galactic exploration. We've studied our own solar system in reasonable detail. We're starting to characterize exoplanets around other stars, but the space between the stars, the interstellar medium where objects like 3I divided by Atlas have been wandering for billions of years, that's still largely unknown territory. We're only just beginning to glimpse what's out there. And maybe that's the real lesson. Not that this particular object is or isn't artificial, not that we've definitively solved the mysteries of its chemistry or trajectory, but that the galaxy is far stranger, far more complex, far more interesting than we imagined. Every time we think we've got it figured out, the universe sends us something like 3I divided by Atlas to shake up our assumptions. There's one more angle I want to explore before we wrap up, and that's the timing of all this. Not the timing of 3I divided by Atlas's trajectory through the solar system, but the timing of its discovery relative to human civilization. Think about it. This object has been traveling through the galaxy for 9.6 billion years. It's passed through countless star systems, witnessed the birth and death of generations of stars, crossed vast stretches of interstellar space, and it just happens to pass through our solar system during the brief few thousand years when humanity exists and has the technology to detect it. The Milky Way is about 100,000 light years across. Our solar system has existed for 4.6 billion years. Modern astronomy has existed for, generously, 400 years. The advanced telescopes capable of detecting and characterizing interstellar objects? Less than 20 years old. The window of time during which we could possibly observe 3 I divided by Atlas is infinitesimally small compared to the object's total existence. What are the odds that this ancient wonder shows up precisely when we're watching? When we have the instruments to see it, the knowledge to recognize it as unusual, and the frameworks to begin studying it. You could argue it's pure coincidence. Space is big. Time is long. Unlikely things happen eventually. We happen to evolve intelligence on a planet that happened to be in the path of an interstellar object that happened to pass by during the century when we happened to be looking up with telescopes. Roll the dice enough times, and rare events occur. Or you could argue there's selection bias at play. We're not special. Interstellar objects pass through every star system occasionally. We're just the first ones in our system who've developed the ability to notice. If 3 I divided by Atlas had passed through 1,000,000 years ago, nobody would have seen it. If it passes through again in 1,000,000 years, hopefully whoever's here will be watching. We're only aware of the objects that arrive during our observational window. That creates an illusion of coincidence. Both of those arguments are reasonable. But there's a third possibility that's harder to shake once you consider it. What if the timing isn't random? What if objects like 3 I divided by Atlas are responsive in some way? Not necessarily controlled by intelligent operators actively steering toward inhabited systems, but maybe programmed with detection protocols. Maybe designed to alter course or behavior when encountering signs of technology, radio emissions, atmospheric pollution, artificial satellites. The spectroscopic signatures of industrial civilization. If you're sending probes to explore the galaxy, you wouldn't visit every star. You couldn't. There are too many. You'd need some kind of triage system, some way of prioritizing targets. And the most obvious criterion is, does this system show signs of interesting activity? A probe passing through a system could detect electromagnetic emissions from a young technological civilization. It could make minor course adjustments to ensure a trajectory that allows close observation of inhabited planets. It could time its perihelion passage to occur when observation platforms are most developed. And from the perspective of beings on that planet, it would look like an incredible coincidence. An ancient object just happening to show up at the exact moment in history when they're ready to see it. This is speculation, obviously. There's no evidence for responsive behavior from 3 I divided by Atlas. No confirmed course corrections, no transmissions, no unambiguous signs of targeting. But the geometry of its trajectory, the timing of its closest approaches to multiple planets, the solar elongation at Perihelion that made it hard to observe from Earth but easier from Mars-based instruments, all of it has a pattern. And patterns make us look for explanations. Maybe it's coincidence, maybe it's selection bias, or maybe it's something else. We don't know yet. But the question is legitimate enough that researchers are taking it seriously. Let's talk about what comes next in terms of public awareness and societal impact. Because discoveries like this don't stay confined to academic journals. They ripple outward into public consciousness, media coverage, cultural narratives. Oumuamua became a cultural phenomenon. It showed up in news headlines, YouTube videos, podcast discussions, even science fiction stories. The public was fascinated by the idea of an interstellar visitor, even if the scientific consensus was that it was probably just a weird rock. Avi Loeb's suggestions that it might be artificial, while controversial in academic circles, captured public imagination. People wanted to believe there was something more going on. 2 I divided by Borisov, by contrast, didn't generate as much excitement. It was more clearly a comet, more familiar in its behavior. The public narrative was basically cool, another interstellar visitor. This one's less weird. Important scientifically, sure, but not culturally provocative. 3 I divided by Atlas is different. It's generating Oumuamua level public interest, but with the added weight of being the third example. 1 weird object is an anomaly. 2 weird objects is a coincidence. 3 weird objects starts to look like a pattern, and people are noticing. Social media discussions about 3 I divided by Atlas are more intense than they were for previous visitors. The industrial nickel emissions get attention because they're easy to understand and inherently provocative. This comet is emitting a metal that only exists in factories on Earth, is a headline that writes itself. The trajectory geometry resonates with people who are inclined toward mystery and conspiracy. Statistically impossible alignment with planets sounds like something from a thriller novel. Science communicators are walking a tightrope. On one hand, 3 I divided by Atlas is genuinely interesting and worth talking about. The observations are real, the anomalies are documented, the scientific questions are legitimate. On the other hand, there's a responsibility not to oversell the artificial hypothesis without sufficient evidence. The line between this is weird and we don't fully understand it and this might be aliens is thin, and it's easy to slip across it accidentally. Some communicators are leaning into the mystery, emphasizing the unexplained aspects and letting audiences draw their own conclusions. Others are more conservative, focusing on the natural explanations being explored and downplaying the more speculative interpretations. Both approaches have merit. The former engages public interest and excitement. The latter maintains scientific credibility and avoids premature conclusions. The reality is that we're in a transitional moment. For the first time in human history, we have the technology to detect and study objects from other star systems. We're discovering that those objects are weirder and more diverse than we expected. And we're grappling with the possibility, however remote, that some of them might not be natural. That's a profound shift. It changes the conversation about extraterrestrial intelligence from maybe they're out there somewhere to maybe they've already been here repeatedly and we're just now noticing. It raises questions about how we should respond if we confirm that an interstellar object is artificial. Who speaks for Earth? What protocols exist for communicating with or studying non-human intelligence? Do we even have frameworks for that? These aren't hypothetical questions anymore. They're becoming practical concerns that we need to think about seriously. And 3 I divided by Atlas, whether it's natural or artificial, is forcing that conversation. There's a concept in philosophy called the Fermi paradox. It's named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox goes like this. The universe is vast and old. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Some of those planets should be habitable. Life should be common. Intelligence might be rare, but even if only a tiny fraction of habitable planets develop technological civilizations, the sheer numbers mean there should be millions of them across the galaxy. So, where are they? Why haven't we detected any signals? Why haven't we found any evidence of their existence? Why does the universe seem so empty? There are dozens of proposed solutions to the Fermi paradox. Maybe intelligence is incredibly rare. Maybe civilizations self-destruct before they can spread. Maybe interstellar travel is too difficult or too expensive. Maybe they're out there but deliberately avoiding contact. Maybe they exist in forms we don't recognize or can't detect. Or maybe, and this is where 3I divided by Atlas becomes relevant. They're all around us and we've been misinterpreting the evidence. What if the galaxy is full of ancient probes? Billions of them, sent out by civilizations over billions of years, wandering through interstellar space on multi-million-year journeys. Most of them inactive or barely functional after eons of travel. Some of them still operational, still gathering data, still transmitting back to home systems that might not even exist anymore. From the perspective of a civilization launching these probes, it makes sense. You can't travel the galaxy yourself, at least not quickly. Biology is fragile. Lifespans are limited, but machines can persist. They can coast through interstellar space for millions of years using minimal energy. They can visit thousands of star systems over the course of their operational lifetime. They can send data back through long-range communication systems or store it for eventual retrieval. It's a slow way to explore the galaxy, but if you have billions of years, slow is fine. And over those timescales, you saturate the galaxy with probes. Every star system gets visited eventually, multiple times by probes from different civilizations spanning different eras of galactic history. From our perspective on Earth, we're just now reaching the point where we can detect these objects. We're calling them asteroids and comets because that's what they look like from a distance. But maybe some of them are artifacts? Ancient machines, so old that they've been eroded and modified by interstellar weathering until they resemble natural objects. Still functional enough to follow programmed trajectories and respond to certain stimuli, but degraded enough that distinguishing them from rocks requires close examination. If that's the case, then the Fermi paradox isn't really a paradox at all. They're not hiding, they're not avoiding us, they're here. We've been looking at them through telescopes for years, classifying them as natural phenomena, filing them in catalogs. We just didn't realize what we were looking at. 3I divided by Atlas might be one of those artifacts. Or it might be a natural comet that happens to be weird. But the possibility that it's artificial is no longer dismissible as pure science fiction. It's a legitimate hypothesis that needs to be investigated with the same rigor we apply to any other scientific question. And if it's true for 3I divided by ATLAS, it could be true for other objects. Oumuamua, 2I divided by Borisov. Maybe even some of the asteroids and comets in our own solar system that exhibit unusual properties. Maybe the galaxy has been full of visitors all along, and we're only now developing the intellectual and technological frameworks to recognize them. Let's pivot to something more concrete. What would confirmation look like? If 3I divided by Atlas is artificial, how would we know for certain? The gold standard would be detection of a signal, an electromagnetic transmission, a laser pulse, any kind of intentional communication. If 3I divided by Atlas started broadcasting, that would settle the question immediately. But so far, nothing. Radio telescopes have been pointed at it. No signals detected. It's silent. The next best thing would be clear structural evidence. If we got close-up images showing geometric patterns, manufactured components, anything obviously technological, that would do it. The Mars orbiter observations were the best chance for that. But as mentioned, the preliminary results show a rough, irregular surface consistent with a natural body. No smoking gun. Chemical evidence is trickier. The nickel emissions are suggestive but not definitive. If we detected other industrial compounds, synthetic materials, isotopic ratios inconsistent with natural processes, that would strengthen the case. But even then, you'd have people arguing about exotic natural chemistry. There's always wiggle room for alternative explanations. Behavioral evidence would be compelling. If 3I divided by Atlas made course corrections, if it deployed anything, if it performed maneuvers that couldn't be explained by gravitational forces and outgassing, that would be hard to dismiss. But again, we haven't seen anything like that. Its trajectory is unusual, but not impossible for a natural object. The frustrating reality is that proving artificiality is much harder than proving naturalness. To confirm it's natural, you just need to show that all observed properties can be explained by known astrophysical processes. That's difficult, but achievable with enough data and creative modeling. To confirm it's artificial, you need unambiguous technological signatures, and those are much rarer and easier to miss. It's asymmetric. A natural object can look weird without being artificial, but an artificial object trying to look natural would succeed most of the time. Unless you get very close, examine it in detail, and happen to notice the tells, you'd classify it as a comet and move on. So where does that leave us? With uncertainty. And that's frustrating for people who want definitive answers. But it's honest. We don't have enough data yet to be certain either way. We need closer observations, better instruments, more time. And maybe we need to get lucky. Maybe the next interstellar object will be less ambiguous. Maybe it'll have obvious technological features or transmit a signal or do something unequivocally artificial. That would clarify everything. But relying on luck isn't a strategy. What we really need is a systematic approach to studying interstellar visitors, protocols for rapid detection and response, space-based assets positioned for intercept missions, international cooperation to pool resources and data, and a willingness to seriously investigate the artificial hypothesis when warranted, without dismissing it out of hand due to discomfort or controversy. 3I divided by Atlas has shown us that these objects are accessible. They're coming through our neighborhood on a regular basis. We can study them if we prioritize it. The question is whether we will. I want to end by zooming out one more time and thinking about what this all means in the largest possible context. We live in a universe that's 13.8 billion years old. Our galaxy has been forming stars for 13 billion years. Planets have been forming around those stars for billions of years. Life in some form could have emerged billions of years before Earth even existed. Intelligence could have arisen, built civilizations, explored the galaxy, and gone extinct multiple times over across that vast timescale. We're late to the party, cosmically speaking. We're showing up in the final hours of a billion-year-long gathering, and we're just now starting to look around and notice the furniture. 3I divided by Atlas is a piece of that furniture. Whether it's natural or artificial, it's been part of the galaxy for almost 10 billion years. It's older than our sun, older than our planet, older than life on Earth. It's seen the galaxy evolve through eras we can only study through distant astronomical observations. And now it's here, in our solar system, available for us to examine. That's remarkable regardless of what it is. But if it's artificial, if it's a relic from some ancient civilization that explored the galaxy billions of years ago, then we're not just studying astronomy. We're studying archaeology, galactic archaeology. The study of civilizations so old that their stars have burned out, their planets have been consumed or scattered, their very identities have been erased by time. All that's left are their artifacts. Probes sent out when the galaxy was young, still wandering, still functioning in some degraded capacity. carrying fragments of data and design that encode information about their creators. Not deliberate time capsules, but accidental ones. Machines that outlive their makers by billions of years. If we could decode that information, if we could extract from 3 I divided by Atlas some indication of who built it and why, that would be the most profound discovery in human history. It would tell us that we're not alone, that we've never been alone, that intelligence is a recurring pattern in the universe that transcends any single species or civilization. It would also tell us something sobering, that civilizations, no matter how advanced, are temporary. They rise, they explore, they build, and eventually they fade. What remains are their machines, wandering the galaxy like ghosts, outlasting everything else. That's a beautiful and melancholy vision. It's also, potentially, our future. If humanity survives long enough, we'll send our own probes into interstellar space. Some of them are already out there. Voyager 1 and 2 are heading toward the stars right now, carrying golden records with messages from Earth. In a few 100 million years, those spacecraft will pass through other star systems, silent and cold and ancient. If there are civilizations around those stars, they'll detect Voyager the same way we're detecting 3 I divided by Atlas. They'll wonder what it is, they'll study it. They'll ask if it might be artificial. And maybe they'll wonder, like we're wondering now, if the universe is full of these ancient wanderers, messengers from civilizations long gone, still traveling, still carrying their stories across the galaxy. So here we are, October 2025. 3 I divided by Atlas is moving away from the sun, heading back into the outer solar system and eventually beyond. We've gathered unprecedented data. We've documented anomalies that challenge our understanding. We've asked questions that don't have easy answers. The object that broke every rule Oumuamua followed has, in turn, broken the rules we thought we understood about interstellar visitors. It's shown us that the galaxy is stranger than we imagined. It's forced us to expand our thinking about what's possible, what's natural, and what might be artificial. We don't have final answers yet. Maybe we never will. But we're asking better questions now. We're looking at the cosmos with fresh eyes, recognizing that our assumptions might be wrong, that the universe doesn't owe us easy explanations. And that's valuable, because the moment we think we've figured everything out is the moment we stop learning. 3 I divided by Atlas is a reminder that there's still so much we don't know. So many mysteries waiting to be discovered. So many possibilities waiting to be explored. Whether it's a comet or a probe, whether it's natural or artificial, 3 I divided by Atlas has already succeeded in one important task. It's made us wonder. It's made us curious. It's made us look up at the night sky and realize that the space between the stars isn't empty. It's full of travelers, ancient objects on impossible journeys, each one carrying secrets from distant times and places. We're just beginning to meet them. And every encounter teaches us something new about the galaxy we inhabit and our place within it. The 9.6 billion-year-old wanderer is leaving now, disappearing into the darkness beyond Neptune. But its legacy remains. The questions it raised, the anomalies it presented, the possibilities it opened up, those don't disappear. They grow. They expand. They lead to new observations, new missions, new discoveries. And someday, maybe soon, another visitor will arrive. Another object from the space between the stars, carrying its own mysteries. Maybe it'll be even stranger than 3 I divided by Atlas. Maybe it'll finally give us the definitive answer we're looking for. Or maybe the answer isn't a single revelation, but a slow accumulation of evidence, a pattern emerging from dozens or hundreds of observations, A realization that creeps up on us gradually until one day we look back and see that everything changed and we barely noticed it happening. Either way, we're living through a historical moment. The moment when humanity stopped being confined to a single solar system in its awareness and started truly encountering the broader galaxy. When objects from other stars became not just theoretical possibilities, but physical realities we could study and touch. 3, I divided by Atlas is part of that transition. A comet or a probe, a rock or an artifact, natural or artificial, it doesn't matter which in some fundamental sense. What matters is that it came from out there, from the vast unknown, and briefly intersected with our small corner of space. And for that brief moment, we paid attention. We looked, we studied, we wondered. That's what makes us human, that capacity for curiosity, that drive to understand, that willingness to ask uncomfortable questions and follow the evidence wherever it leads. 3, I divided by Atlas challenged us. It broke our rules. It defied our expectations. And in doing so, it reminded us why we look up at the stars in the first place. Because there are mysteries out there. Ancient mysteries, strange mysteries, profound mysteries. And we're finally becoming capable of investigating them. The journey is just beginning. If you want to see what we discover next, subscribe.